Hey guys, so thank you all so much for coming today. We are going to be the first ones to kick it off, so hopefully we don't have any AV issues. If we do, somebody message Michelle or Landon, who is in our booth, and he can kind of take care of that. There should be a question and answer tab, so at a chat tab. So if you guys have questions, feel free to put your questions into the chat tab. Landon will continue letting people in, and then also kind of monitoring that so we can answer some questions while the demo is going. Another thing is, normally I do these very kind of open-ended, where it's a discussion, kind of figuring out what you guys like to do for your research and tailor it to that. Today I'll be a little bit more generic because I think having 35 people trying to talk over each other might be a little bit difficult. So definitely keep your questions, and at the end we'll open it for Q&A and just talk about Ripple systems and how they can actually help your research. So to start, we have several different kinds of processors for actually doing your research. So the one I have here with me today is our Summit processor. So the beauty of what Ripple does that's a little bit different than, thanks Landon, the QR code that is actually moving around my face right now will enter you to win a Switch, Nintendo Switch. So if you're interested doing those survey questions, it shouldn't take more than 5 minutes. And then at the end of my demo today, we'll announce who will be winning that, and then you'll be contacted by Ripple to get that sent out to you. So on that note, I will get started. So with the Ripple system, what we are is a data acquisition system. So we kind of help our researchers go from where they choose the electrodes that work for their research questions, be it in the cortex, be it deep brain. We then provide the workflow from getting those signals out of the brain and into your hand so that you can do your data analysis and really answer those scientific questions. So our processors are portable. So that's one of the big things that Ripple really focuses on. And so this is our 512 channel processor. So these processors are great for both animal research and human research. This is actually our human version. With the pandemic, as I'm sure you all know, we have limited equipment that we can have in our actual houses. So this actually is similar to what will be called the Trek in the animal space. And so this is a portable processor that allows you really to do up to 512 channels. As you can see here, I have 256 channels connected. And so when you're at the actual electrode, what we have are front ends. So a lot of people will be familiar with what's called head stages. And so these are those front ends for us. So for us, we actually do all the digitization and amplification on the animal's head. So if you have a primate experiment, for instance, rather than having a cable that then takes the analog signal to where your preamp is, now you can do all that right on the head to limit the amount of noise that's either from motion artifact, electromagnetic fields, a lot of these monkey experiments, and a lot of the experiments you guys do, be it monkey, human, or rodent in the NCM world, a lot of them have a lot of other tools that are involved. For instance, a kin arm system or a Moog system where your whole experimental platform is being moved, or some people even have their animals doing mobile walking experiments. So having the amplification and digitization at the actual front end is really critical in terms of getting clean and high fidelity data. So we have several different options for our different kinds of front ends. That's one of the beauties of the multimodal systems that Ripple offers. And so the ones I have here are, one is for our 32 channels of recording only. So this one is a lot smaller. You can fit several of these on the head to connect to Omnetics-based electrodes. We also make adapters for any kind of electrodes that you guys intend to use. We also then have our record and stim. So what separates this from a lot of our competitors on the market is that this device itself has 32 independent current sources. So whereas a lot of systems, when you want to do stimulation and recording, you have to choose which channels will be dedicated for stimulation and which channels will be dedicated for recording. With the Ripple system, you can actually turn on stimulation on all channels simultaneously while recording from those same channels. So you don't have to, before your experiments, decide these 16 channels are stim only, these channels are record only. You can record from all 32 and then decide to stim on whatever channel whenever you want. So that's one of the big things. And what's great about Ripple, and one of the reasons I wanted it as a grad student, I always say the first demo I ever did was trying to get my boss to buy me a Ripple system for my own research. And so for that, like, you can actually change your stimulation parameters on the fly. And I'll show you that later in my demo once I get to the software. And so it's really just key for these closed loop applications where you want to use recorded neural data to then trigger stimulation or trigger paradigm changes, et cetera. So that's really one of the strong suits of the Ripple system. So we have those two front ends, so our recording and our stimulation. If you're doing rodent experiments, we have something that's a lot lighter. I'm going to try to hold it up to the camera. This is less than a gram. This is our 16 channel record and stim front end. So it's very light. It's, as I said, less than a gram. It's one of the smallest on the market, and it does give you the same 16 channels of stimulation, arbitrary stimulation, simultaneous, that our Nano 2s and Nano 2 Plus stims have. So it's really just a smaller, more rodent-friendly version of the same technology you would be using with any of your Ripple systems. I will briefly touch on our new human line, and then kind of move into the software. So for humans, we have something that's also very similar to our Nano 2 Plus stim. This is our Micro 2 Plus stim. So it gives you stimulation amplitudes up to 1.5 milliamps per channel. Again, 32 independent current sources, all safe for human use. None of it is FDA, but it is all 60601 safety. And then the final one that we have here for human, we have our EEG, our new EEG front ends. So these are now for our EEG non-invasive applications. And then for invasive applications, we have this is our EEG plus TES front end, but we have a macro plus stim version that gives you 15 milliamps of stimulation, which is more well suited for macro electrodes that are used in many clinical research applications. So I'll put these on the floor because that is what my life is these days. And then finally, one of the front ends we have that's really a cool thing and that's relatively new is our fully implantable EMG or EEG front ends. Let me try to get this in there. So this is something, I know Brian Cornell actually just did his first implantation with this, which was really exciting. We have several that a lot of the NCM members actually are the ones who use these. Steve Scott has a different version, but it's very similar. And so what this version does is it's very thin and it has a magnetic connection to a transceiver, which then, so if this is under the skin, this one is an empty one, but if this is under the skin, I'm about to do my experiment, I can just kind of click in on a date, of course, if I get it the right direction. I can just click in, so the monkey skin would be in between, the monkey, the pig, we have this in several different models, would be between, and then the data is actually connected over IR. So the data is then transmitted to this transceiver, which then communicates with your processor and gets you all of that data. So the beauty here is the ability when you have EMG studies, a lot of times, and as a lot of you know, the head cap and wherever the percutaneous connection is can end up causing a lot of problems. And so what this does is it allows you that when your animal goes back into the cage, you have no percutaneous connections. The animals can't pick at those wires that are routed all the way down the arm or down through the legs. Now you really have the ability when it goes into the, when they go back to their cage to not provide that infection risk. So this is one which we can talk about this in more detail, and I'm happy to talk about this after, that just to show that grad students are also able to do these soldering onto these. So I actually soldered this one together and then backfilled it with epoxy. So this actually is a really cool tool that allows you to use whichever electrodes are best for your experiments and use them in this implantable package. So now that we've kind of gone over the hardware, I will start by getting us into the software. Let me plug in my systems again. The system is hooked up. I have it connected to power and to the Wi-Fi connection. This system, the Trek and the Summit processors are able to connect over Wi-Fi. So if you're collecting signals and you want your animal to be freely mobile, or if you are trying to limit wires, let's say in the OR, you can actually have your communication go over Wi-Fi. I won't be able to show that here because if I disconnect from my house Wi-Fi, we won't be able to connect anything anymore. So I have this now plugged into a Nano 2, which you can see here, a Nano 2 Plus stim, and then an additional Nano 2 Plus stim for some of the demos that I want to be doing. So this is kind of the main hub. Our software is, unlike some of these other software platforms where you get a lot of analysis tools, our software is designed for acquisition. And so here's where you decide kind of what signals will be coming into the processor itself. So the processor is a Linux-based computer. All of the computing that you do happens on here. You're just sending the commands from your actual computer. So if you're doing spike sorting, things like that, which we'll get into, all of that is hosted on this processor, giving you the fastest turnaround times and also the fastest visualization. So what we have here is what actually determines what signals come into the processor itself. So we have our raw, which is because we're using the nanos, this is 30 kilosample per second data stream. We have our LFP, which is a 1 kilosample per second data stream and allows you to look at different kinds of filtering that we have. Our high res also allows you to look at different filtering. These will be named the display channels in our next release of our software, just because you'll be able to choose which kinds of sampling frequencies you want on those channels, and then also which kind of filters you want. So there are a lot of options here for providing you with those different filters. So I know this is a little bit small, but you can see on each of our front ends, I can choose several different streams and record them simultaneously. So I can do filtering in real time online and then see what those signals look like offline. So if I do offline filtering afterward, I can see how similar is that to what I was seeing and what I expected my filters to be doing during my actual experiments. So that's something that's really nice here. We'll talk a little bit more about this stimulation, our fast settle technology, as we get into the stimulation portion of the demo. And so this also gives you the ability to record your configuration files. So if you've sorted all your spikes, they're not going to really change day to day if you're using a chronic electrode array. So you can kind of load your sorts from the day before. You can load your configurations if you've turned off some channels because they're bad. As you'll see, actually, the hardware I'm using, I have a bad channel 13 on A. So as you see, I've loaded my configuration to have channel 13 turned off. And so these are things that really allow you to customize and not have to go through all the steps of restarting during every experiment. So that's kind of the main landing page. There are some things here that I'm not going to cover just due to time and the nitty gritty. I kind of want to keep this a little bit more high level, but essentially this is where you're able to set your configurations. You're able to set global thresholding. So if you want your thresholds to be the same on every channel versus on a per channel basis, you can set your filters and your fast settle. And so what's great here too is you also have some hardware filter options, which I won't go into. They're different per front end. And that also allows you to kind of set those hardware filters if that's something you're interested in versus having the software filters. So then we have our applications, and here's where you have your application tools. We have our raster, which I opened here. With raster, you're able to essentially change it so you're clipping if you'd like. So after your range, you can change what your range is. You can change the speed, how you want to visualize it. So here I have it so that we have all of our LFP, then all of our raw, and then all of our spiking channels. So if you want the simple raster that you're used to seeing, this gives you that option as well. And one of the things, as I'm going through the GUI software, we will also go in, we have a Matlab API, a Python API. So any kind of visualization you want to do, you can. We have lots of people who are actually porting things into LabVIEW so that they're able to see their signals with their behavioral control paradigms. So there are really just tons of options that you can do with the Ripple system. So let's go back to the view that I like, which is looking at each channel. So I have my raw, my LFP, and then my spikes per channel. So I can speed things up, slow things down, and really have a lot of freedom here. So if you're doing spike recordings, we also have our spike grid, which this is what I didn't change. So as you'll see, this last bank here, I have that connected to just a light board. This is one that I'll use for my demos later on. And so it will look like garbage because it is garbage. So essentially we can see that down here, and you can see that it's all live when I'm touching that electrode connection. You're able to see that change as well. So this is a really fun tool here too. You can kind of change how many spikes that you want it to hold per time. I like the heat map option if you're looking, because this is a map file essentially, you can create a map file for this that goes along with whatever your electrodes are, be it they're linear probes. You can turn this heat map and spike grid into a linear orientation. And then you can kind of see with this heat map, where are your activity? Where is the activity actually happening on your array? And so this is one thing, it doesn't show up that well with this high spiking activity, but that's something you can change your color map. And as we've gotten into the EEG world, we also have the ability to do continuous impedances and look at that. We have heat mapping there. So all of that in intense map files are just text files that you can kind of create, and we can help you create. So once you have something like this, let's say we want to look at channel 26. I now also am able to see my spike scope. And so this is one that's really useful for both sorting and for actually setting your threshold. So these, I mean, spikes are gorgeous, they're fake. And so for here, you can definitely see that on all channels, having a global threshold is sufficient for detecting those spikes. However, if you had a cell, let's say, that had a really low spike that you wanted to capture, or if you wanted to only capture those really big spikes, you can set this up where you're only capturing those few spikes that cross these lines. So for if I want this biggest one, for instance, I'm only now going to get one because I've changed the threshold on that. So if you change the thresholds on this per channel basis, they will also stay as part of your configuration file. So if we want to go back to catching all of those spikes and show spike sorting, it's also something that's quite nice to do. I'm going to move this so I don't get the zoom. So I can enable sorting, and then we use a hooping method. So essentially you get 4 hoops per spike, and you're given up to 4 spikes or 4 neurons per channel. So if I want to say that it has to go through there, let's do another loop. It also has to go through that one. We want to sort this to be here. So I really have the option, and I can do this now on every channel. So I can then go through and I'll see those sorts on my spike grid as well. So if I then put some more in here, you can see that those stay. And so what's really great here is if you have multiple people, or if let's say you're doing 512 channels, that's a lot of channels to sort, especially while the animal is sitting there. And so what you can do is have the actual Nomad processor or Trek processor hooked up to multiple computers and have multiple grad students or multiple people sorting at the same time. Because sorts are actually saved to the processor and not to the computer, if you have multiple computers that are sorting, each computer will see the other person's sorts because they are being logged into the system itself. So that's another thing that's really great in terms of getting those initial days of data collection after you kind of let the array settle. It gives you that opportunity as well. While we don't have threshold and online sorting mechanisms such as PCA or anything like that, our data does work with Plex on offline sorter, and then also with the Neuro Explorer module and Spike 2. So all of that allows our data form to actually be taken directly in to get you those tools for offline spike sorting. Another thing that our system does now is save data to an EDF plus file. So if you're doing EEG, or if you're using things like EEG Lab, M&E, Curry, for any EEG experiments, you also have that option of saving as EDF. So that's kind of the main acquisition tools. I will show cameras first and then STIM, and then we'll take questions. So if I open back up here, we also have an impedance module. So this allows you to record your impedances in real time. So if I were to, for instance, do, I don't know what the resistance of this actually is. If I just do the Nano 2 and then start, I'm able to get my impedances pretty quickly. So that's just another thing. Again, this is not the same as using kind of like an Autolab potentiostat or what's it called, the Nano Z, or any of those that are meant for impedances. What this is meant for more so is to see that your impedances are consistent day to day. So the recordings are very consistent. I would say that they are more consistent than they are accurate. But when you're looking for things like infection or the tissue electrode interface, this is a really good tool to kind of give you that gut check. And then before I get into STIM, I'll do the video controller. So this is a new tool that we have that's pretty cool, I think. So this was something that we developed when we were starting to really focus on the rodent space more, but I think that there's a lot of applications for monkey experiments where this could also be very useful. And then also in the human space for epilepsy monitoring, it's great. So you get to look at all the cameras you have hooked up, and then you choose which cameras you want to connect to. So I've connected to my computer over here's camera. So then if I double click, now that I'm connected, I have live video that I can record in addition to all my neural signals. So this is just a simple USB camera. You can have, so far we've tested up to 6 cameras simultaneously. So we are still in the process of, we haven't had anyone ask for more than that, but I don't think that there would be a real reason why it wouldn't allow you to. So you can just kind of go through, you'd have all your devices here. So you can see the different angles of your cameras. And in the rodent space, this is really helpful if you want to do a recording. We also work with stolting for any maze so that you can do offline characterization of your experiments after the fact. So, but what's great about this as well is that we have a playback function. And this is something we plan on extending to the signals, not just to video. But if I go to playback here, and so essentially when you would be recording, which for saving, you would just choose to save your camera data as well. And that would give everything all on the same folder. So I recorded a little ugly video earlier just to show playback. So you can browse and then actually have your data file. So if I open this now, I can watch my little video that I have here, but I can pause it and say like waving. And let's say that I'm waving with a score of 5 and save that. And now I have a metadata file that's also being saved in addition to the same folder where my data is saved, my raw data files, my digital data files. I now also have a file that says which processor clock time I've recorded that happening. As a primate researcher, this for me would be something if my monkey was sleeping in between trials and I wasn't able to get him to work. I could put those kinds of notes in and then either choose to ignore that data or to specifically look at that data to look at inter-trial intervals and really just have a better recording of data. And I can choose my frame count. So if I want to go back frame by frame, for seizures, this is really important. So if you see a seizure, you can mark when that seizure happened and give it a seizure score. So there are lots of different opportunities that you can do with this playback feature. And then finally, we'll get into the good stuff, which is STIM. And so if I open my STIM window here, you guys all have coffee. I have soda. I'm a morning soda kind of person. But let's see if we go into the STIM window. So there are a lot of options for STIM with our system. And the biggest thing here is that with the really complicated STIM applications, we recommend using our Matlab or our Python API. Our GUI will give you the opportunity and the option to STIM. But what you'll see here is we have, for instance, our waveforms are going to be a biphasic. You can have them be a different kind of charge balanced biphasic. But you essentially have a biphasic pulse that you're able to do with the Ripple GUI. So one of the things I do want to show with the GUI, and while you can do more complicated STIM patterns, we have this multi-channel STIM where you can pull down certain channels, create STIM scores, but really when you're going to get complicated, to make it easier is by going to our API. So first I will show kind of with our fast settle technology off. So fast settle, what it is every channel has an independent current source and then 2 amplifiers. You have your recording amplifier and your simulation amplifier. What we do is, and then you have your electrode, of course, connected to eventually going to ground. That's in the body. And so what we do is most of the time when you're recording, you're going through your recording amplifier. And when we decide to do this fast settle, when you're stimulating, what we do is we disconnect the channel from the recording amplifier and bring that over to the STIM amplifier for however long you specify. So essentially, your recording amplifier isn't going to saturate because it's not going to see that current. And so that's kind of how we've done it on our Nano 2 plus STIM, our Pico 32 plus STIM, our Pico 16. If you go into our macros, which are and our EEG plus DES, we instead give you the ability to ground out channels directly after STIM. So to show you first without fast settle on, none. Let's do here, let's see. Let's do 250 microamps, not milliamps. That would be insane. 250, we'll do 10 hertz to start. And when I STIM, oh, fast settle is definitely still on. Oh, no, I'm clipping. That's what it is. I was like, that looks way too good. Oh, yeah. So what you can see here is I'm now stimulating on channel 213. So that's on my second front end on my 13th channel. So this green channel right here. And so when I stimulate, you see a large artifact that's coming through. And this is understandable. Right now, both of these, all of our recording electrodes are sharing the same ground. The ground is what the STIM is returning through. And so When you then turn on fast settle, and I want to make this so you can also see this down here because it's really impressive. This is one of the things that I think is super cool. Yeah, we'll just keep that off because why not? Sorry, I'm used to having this on 2 screens and I can only share one at a time. So now if we turn on the fast settle, and let's do it for 1 millisecond. So the idea here is you want to fast settle it for long enough that there's not current still on that electrode when you're going back to that recording amplifier, but you don't want to do it too long that you might miss any spikes. So you can go to 0.5 milliseconds is the fastest time we have for the fast settle, but I'm doing 1 millisecond here because that's the refractory period of a spike. I'm expecting to be able to catch the next spike directly after stimulation. And so when I do that, and then I do that same stim pulse, I want it to come back around. You'll see now that it's much better and none of these in the spike grid. So I'll do that again so you can see. So the first time doing it, take a look at channel 13. Channel 213, sorry. This green channel here. So first take a look at that when I'm doing it and you'll see the fast settle artifact, those little things there, but you're really able to recover a lot of your LFP as well as your spikes. But now if you focus, I'm going to do the same thing. And if you focus on the spike grid, what you'll see is that you're able to really keep all of those spikes even during the stimulation. So if I go to actually channel 213, which is the one that I'm actually stimming on, if it will open. So here's that 213 doing the same stim, and I'm not even seeing it on my spike scope. So I'm really able to keep the integrity of those spikes that are happening. And something that a lot of people ask is, what about if you go faster? And so let's do 100 for right now and do that same thing. And I'm still able to really keep those spikes. You can see where there was that little stim artifact, but you're really able to maintain the integrity of your spikes. Here, your low frequency is definitely getting impacted. And that's, again, it's a physical switch. So on channels where you're not stimulating, what we say is, let's say you have an electrode array in one part of the brain where you're stimming, and then an electrode array in the other part of in a different part of the brain. The first thing we would suggest is only fast settling on the channels where you're actually doing stimulation or on neighboring channels of where you're doing stimulation, and not fast settling on those electrodes that are a little farther away. And then if you start to see artifact due to the stimulation, that's when you include the fast settle, because as much as you can keep your data raw, that's just the better option. So that's one thing there that I wanted to show. But so now what I will show is kind of going into the Matlab space of things. So, and showing the closed loop. So we don't need these for now. I'll leave this here because it's cool. So if I go down here, so the beauty of Matlab and our API is it really allows you to do more complex behavior. So if I wanted to, for instance, stim on 3 different channels using our GUI, I would then essentially take, okay, I'm on channel 213, come down, put that in here. Then let's go to 29, make a stim channel, add to the multi-stim. So I can have all of these different stimulation patterns going at the same time on these different channels. And have them all going at the same time, set in a pause and offset beforehand. So you can do complex stimulation through our GUI. However, what's a lot more simple is going into a Matlab and looking at this, for instance, this is our just LED board test. So in this 50 lines or so, and I'm not a great programmer, but in this 50 lines, and Erin Grigsby, I saw her earlier, she can tell you that. But yeah, so with this simple coding here, what I've done is I've said, all right, I want to stimulate on every other channel 3 times in a row and then go through each channel one way and then back. And so you'll be able to look, if you look down here, you'll be able to see it happen. And I'll also hold this up, which I'll be stimming on this front end in with this code. So what you can see is that I'm stimming. Can you actually see it on here?
It's somewhat visible.
Somewhat visible, not super visible, but try it again. Yeah, there we go. Got the right light. But yeah, so you can see that I'm now programmatically stimulating. And that's something that I can choose my amplitudes. I really can choose anything to make that happen. It could be on looking at amplitude. It really does not matter. So what's cooler about this application is when I can do all of that in Matlab, that means I can now do closed loop experiments. So if I go to this, what I have told this code to do is essentially go through and look at this last channel here, channel 64 or 232. And every time that there's a spike in this channel, I'm then going to stimulate on every other channel. And so this really gives me the ability, it doesn't necessarily have to be spikes. It could be, if you want to do power of a certain frequency band, if you're doing ECOG or LFP, you can really look at several different things to do this. Oh, looks like I lost a packet there for a second. But yeah, so you can see that now every time there's a spike, that's occurring shortly after I'm getting that stimulation that's going. And so that's something that allows you to really do all of these things in closed loop. And you can really do any kind of, in Matlab, if you wanted to do averaging, if you wanted to do differences of different channels, you really have the ability to do all of that. And so that's kind of just an example of the closed loop capabilities of the system. But essentially, that's kind of all I've got in terms of prepared material. So at this point, I will stop sharing my screen and take questions.